So thanks for inviting me here to the organizers. It's a principle I'm aware of in organizing and scheduling speakers, that you put the most exciting speaker at the beginning of the day to make sure everybody gets out of bed, and then at the end of the day to make sure people don't go home early. So I'll assume that's why I'm here now. If it's not the case, don't tell me. Right. So my background was I wasn't born a tropical geometer. I started off life as a mathematician in topology. And if you're a topologist, then you kind of imbibe this idea that the thing we should really ultimately try to understand is smooth manifolds. Of course, before you get to understanding smooth manifolds, you find out there are these things called topological manifolds. And some of them are smooth and some of them are not. And there's lots of really interesting deep topology that goes on in the distinction there. And then a little bit further on in your education, you find out that there's this other world that sits in some sense in between, called the PL manifolds, the piecewise linear manifolds. And now we've got these three different worlds of manifolds. And as a topologist, you say, okay, a fundamental question here is, can we distinguish them? How different are these worlds? How similar are they? What distinguishes these? Are there phenomena that take place in one and not the others? So there's the problem. Understand the differences and the similarities. And there aren't a whole lot of tools we have here, but one of the first ones that you might think of is the tangent bundle, right? If you've got a smooth manifold, you can differentiate things. And so you've got a notion of tangent vectors, and these form vector spaces, and that's the tangent space, and that gives you the tangent vector bundle. If you're a topological manifold, then you don't have that extra structure. So there's some sort of tangent gadget, and people call it a tangent microbundle or various things. There are tangent structures there, but they're not honest-to-goodness vector bundles. And similar for PL manifolds. You have some sort of tangential structure, but it's not as nice as a vector bundle. So maybe we'll use the tangent bundle to try to distinguish these things. And as soon as you start thinking about the tangent bundle, you want some algebraic invariants. And the first ones that come to mind are these things called characteristic classes. So when topologists are being educated, characteristic classes are one of the first things they learn. But in algebraic geometry and tropical geometry, you don't necessarily learn that early on. So I'll do a quick review here. There's a tangent space, just in case you want to know what that looks like. Right, so what is a characteristic class? Quick review here. We've got a vector bundle over some base B. And a characteristic class is going to be something which associates to that vector bundle over B a class in the cohomology of that base space B. And it's supposed to be not just any old class, it's supposed to be something which is natural with respect to pullbacks. So I can pull vector bundles back along continuous maps, and I can pull cohomology classes back, and these two operations should equal each other. Right? So in more detail, if I have a map from A to B, I can pull the vector bundle V back to A, and this map F induces cohomology is contravariant, so I have a pullback map from the cohomology of B to the cohomology of A. I have my characteristic class for the vector bundle V, and I can pull it back to get some class on the cohomology of A, and compare that to the characteristic class for the pullback bundle. So that's a different class in the cohomology of A, and this naturality is simply the condition that those two things are equal. So every vector bundle of rank n can be pulled back from something called the tautological or the universal bundle over the Grassmannian of n planes in our infinity. We've got this nice moduli space of rank n vector spaces, and you could pull every rank n vector bundle back from that. So given my vector bundle V over B, there exists something called a classifying map into the Grassmannian, and I can always find an isomorphism of V to the pullback of this universal bundle over the Grassmannian. Yeah. I didn't say it's unique. The classifying map, yeah, up to homotopy is unique. Yeah. Okay, but cohomology only cares about maps up to homotopy, so we're good. Right, so the universal characteristic classes are things that live in the cohomology of the Grassmannian. And we're doing cohomology, you've got to worry about what coefficients you have. So I've got some coefficient ring R there, which we'll talk about in a second. Right, so these universal characteristic classes are the characteristic classes associated with this universal bundle. They live in the cohomology of the Grassmannian. If we take F2 coefficients, then we know exactly what the cohomology of the Grassmannian looks like. It's a polynomial algebra on these things called the Stiefel-Whitney classes. So the ith one lives in degree I, and those generate the cohomology ring. That's all there is. If you take Z coefficients, then the story is a little bit more complicated. And notice this is not an equality, but a containment here. So we have the cohomology contains a nice subring consisting of these things called Pontryagin classes. They go from 1 up to n over 4. And you can do these with either integer coefficients or rational coefficients. If you do rational coefficients, then this is just about an equality, except maybe there's an Euler class which squares to give you the top Pontryagin class, depending on whether 2i is even, let's say, depending on whether n over 4 is even or odd. If you've got integer coefficients, then there's some two torsion in there that's complicated to describe, but more or less everything there is the Pontryagin classes and possibly some two torsion. Right, so the history of using characteristic classes to study this question of distinguishing the worlds of manifolds. Well, Whitney, back in the 40s, the Whitney of Stiefel-Whitney classes, he very quickly pointed out, after defining these classes, that the Stiefel-Whitney classes of the tangent bundle are PL invariants. So if I have two manifolds that are smooth manifolds, so they have tangent bundles, I can look at their Stiefel-Whitney classes. And if I have a PL isomorphism, I don't necessarily know that this PL isomorphism takes the tangent, I don't necessarily know that this PL isomorphism is actually a diffeomorphism, but it will necessarily take the Stiefel-Whitney classes of one to the other. And the reason for this is because there's a combinatorial formula for the Stiefel-Whitney classes in terms of a triangulation. But then things get more interesting when you get up to 56. So Milnor famously constructed these exotic 7 spheres. And in the construction, there was some appearance of Pontryagin classes. René Thom, a couple of years later, showed that for PL manifolds, you can extend the definition of Pontryagin classes as long as you're using rational coefficients. So with rational coefficients, even though we don't have a tangent bundle, we can still define and work with Pontryagin classes of the thing that might be the tangent bundle, but it doesn't exist. Milnor comes back to this, so now 64, and he says, there are some smooth 8 manifolds where these are smooth manifolds, and there exists a PL isomorphism between them that is not a diffeomorphism. And in fact, they are PL isomorphic, and there does not exist any diffeomorphism. And the way he showed this was by showing that even though Thom says they've got rational Pontryagin classes, which are the same because they're PL isomorphic, they are not diffeomorphic because they have different Pontryagin classes over the integers. So they can't be diffeomorphic. So that was a beautiful, amazing result from Milnor. This is the sort of stuff he was doing to get a Fields medal. Novikov, a year later, comes along and says the rational Pontryagin classes are actually topological invariants. So if you have a homeomorphism that isn't necessarily diffeomorphism, this homeomorphism will carry the rational Pontryagin classes of one to the rational Pontryagin classes of the other, even if they have different integral Pontryagin classes. So even applied to Milnor's examples. So that's the history up until 1992, when Gelfand and McPherson repeated what Whitney did for the Stiefel-Whitney classes, but now for the rational Pontryagin classes. So they given a triangulation, they gave a combinatorial recipe for constructing the cocycles that represent the rational Pontryagin classes. Okay, so that's my quick history there. Um, yeah, I think more or less. I mean, yeah, let's say yes. Okay, so the way that Gelfand and McPherson did this was by implicitly introducing yet another world of manifolds in between here. And they called these things CD manifolds. So PL manifolds were supposed to be combinatorial objects, but they realized that they weren't quite fully combinatorial enough. And so CD manifolds do this funny thing of simultaneously being more genuinely entirely combinatorial objects, while simultaneously reflecting the way smooth manifolds work a little bit more closely. So roughly, CD stands for combinatorial differentiable. For a smooth manifold, we've got a tangent bundle that's classified by map to the Grassmannian. Now, if we have a CD manifold, what they said is, well, this is some triangulated object, but it's supposed to be like a manifold, so you have these local patches where it's identified with a piece of Euclidean space. So here is a vertex, and here are 4 triangles that might make a part of a surface. And we've identified this with a patch in Euclidean space, and that means we've flattened it out. And what they notice is that when you have this patch, this local flattening, they call it, then you can look at the edges incident at this vertex, and what you see is some configuration of vectors in a real vector space. So you see an oriented matroid. And then what they noticed is that a CD manifold should be an object where at each, I think it's at each codimension 2 stratum, you have an oriented matroid, and along each codimension 1 stratum, you have a compatibility condition. So these local oriented matroids that you see at different places have to fit together in a combinatorial compatible way. So that's roughly what a CD manifold is. And so it turns out that this CD structure defines for you a map up to homotopy. That's the combinatorial tangent bundle. So that's a map from our manifold into this thing called the Macphersonian. So the Macphersonian is simply the space of oriented matroids. And then what they showed really in their combinatorial formula is that the rational Pontryagin classes can be made to live on this Macphersonian. So this is sometimes called the matroid Grassmannian. What type of space is it's the nerve of a partially ordered set. It's the nerve of the partially ordered set of oriented matroids. Yeah. Yeah. So here's the slide that explains this. It's a good question. I haven't thought about that. That's a very natural question. I should have asked that question, but I haven't. Yeah. Okay. So here's what I just said, answering Martin's question. You anticipated my slide, right? Yeah. Let's see. Okay. So we can go on then. So there exists a comparison map that takes well, you can take a smooth manifold and use a triangulation and combinatorialize it. You can take a real vector bundle and combinatorialize it. And what you get is a map from the Grassmannian to the Macphersonian. Right, so this is a comparison map that compares smooth vector bundles to these oriented matroid bundle type objects. So McPherson was able to define this on an up to homotopy level, and then Laura Anderson came along sometime later and was able to refine that and give a nice point set level construction of this map. But the point set level construction was not entirely easy to construct. So McPherson points out that this comparison map, when k is equal to 1 or 2, so dimension 1, dimension 2 subspaces, or codimension 1 or codimension 2, in all those cases, the comparison map is an equivalence. So the Macphersonian, the matroid Grassmannian, is equivalent to the ordinary real Grassmannian. And then McPherson says, otherwise, the topology of the matroid Grassmannian is a mystery. We don't know. Okay, so then in 2003, Dan Biss, in his PhD thesis at MIT, famously published in the Annals a proof that this is, in all cases, a homotopy equivalence. Amazing paper. There's only one problem. Turns out it's wrong. It had to be retracted. It had to be retracted in an awkward situation where he was running for a political office, and his political opponent said, "You can't believe anything this guy says. He's published results that are wrong." Not that time, but in subsequent elections, he has had a low-level political career, but he's been relatively successful at that. Yeah. Yeah, so the problem now is that the question is still open. And because of this history, I think people have been a little bit hesitant to touch it. And nobody really wants to get involved, unless you're foolish like me. All right, so I don't want to try to prove or disprove the conjecture, but I'm going to come at it from the side a little bit and say, well, let's think about some of the structure that the real Grassmannians have. So some of the nice homotopical structures that are there, and see if the matroid Grassmannians have those same structures. So here's the structure that I like to think about. K-theory was something that's near and dear to my heart. So the starting point of K-theory is direct sum, right? I can take the direct sum of two vector spaces. And if I have an n-dimensional space sitting inside a big ambient space and a k-dimensional space, and I direct sum them, well, I get something of dimension n plus k, but the cost is it now lives in the sum of the two ambient spaces. Fortunately, infinity plus infinity is infinity. So you can choose an identification of two copies of R infinity back down to one copy, and you get an induced map down to here. Okay, so we have something that looks kind of like a monoid multiplication operation given by a direct sum. Sorry? Where's the... Oh, sorry. Ignore that plus. That shouldn't have been there. That was a typo. Right. So this makes the disjoint union of these Grassmannians into a monoid. Now, if you have a monoid, you ask, well, how nice is this monoid? Is it associative? It turns out this operation is not quite associative. Maybe I shouldn't quite call it a monoid, but a semigroup, depending on your terminology. It's not quite associative on the nose. Is it commutative? Now, it turns out it's not. If I swap the two sides, I get something which is a different map. But fortunately, it's commutative up to homotopy. So it's commutative, and it turns out also it's associative up to homotopy. Oh, that's good. Even better, it's what's called E infinity. So this is something that topologists, homotopy theorists, get really excited about. It's not just commutative up to homotopy, it's commutative up to all higher homotopies. So if I have three terms and I try to combine them, I've got a few different ways of doing this, and then I can find two different homotopies between the different orders of multiplying three things together. And then I can find a homotopy between those homotopies. And then when I go up to 4 or 5 terms, then I can find homotopies between my homotopies, between my homotopies, and so on. So it turns out that for any number of terms, there's a contractible space of different ways of different orders of multiplying them. So that's what E infinity means. Right? So topologists love this because E infinity structures are very close to what are called generalized cohomology theories in the world of stable homotopy theory. So in this case, this E infinity structure leads directly to this thing called real K theory. So this was the first example. Well, it was the first example that was discovered in generalized cohomology theory was complex K theory. And then the immediate next example was real K theory. So this was the work that Atiyah did.
First example.
The first example I said of a generalized cohomology theory that's not not ordinary cohomology. You're a real stickler for terminology today. Right. So we can do the same sort of thing with the matroid Grassmannians, right? I've got a direct sum operation for oriented matroids. So I can take two oriented matroids on two distinct ground sets and put them together and get an oriented matroid on the on the disjoint union of those two ground sets. And unfortunately, I've got the same fact here, the good old accountability that says, Cantor tells me that natural numbers union the natural numbers is just a copy of the natural numbers again, but I have to choose an identification, and there's some choice involved there. So as soon as I choose one, I get an induced map down to the Macphersonian on the ground set, a single copy of the natural numbers. So the collection of all these maps fits together to make these things into a monoid. And then the theorem that I want to talk about today is, as for the real Grassmannians, this thing is an E-infinity monoid. So it's commutative and associative up to all higher homotopies. All right, so that's the theorem. Consequence of that, yeah?
Is there any dependence on this identification of N union N?
A contractible dependence. Right. Yeah. So consequence of, if Macpherson's conjecture were true, then this would be an immediate corollary. But we don't know if Macpherson's conjecture is true or not. So for the meantime, we have to settle for saying, well, the real Grassmannians and the matroid Grassmannians, they both have this nice E-infinity structure. And I haven't written this down yet, but I believe it's true that the comparison map is an E-infinity morphism. So it respects these structures. All right, so let me talk about how I construct this E-infinity structure. So we've got matroids, and we've got these two nice enhancements of matroids. On the one hand, you can go to the tropical world and talk about valuated matroids, or we can take the left path and talk about oriented matroids, where we add some sign data in. So I'm going to think of oriented matroids in terms of the chirotope axiom set. So chi, a chirotope, is a map from, at the moment here, E is my ground set. So I've got, it's a map from E to the N to the set plus, minus, and 0. And it's an alternating map. So if I swap two entries, it changes by sign. And it satisfies this exchange property, which says if I have k plus 1 things here and k minus 1 here, and I take one of the x's and I move it over to the other side, and I look at all the possible ways I can lift one of the x's from the left to the right, then either these products are all 0, or if one of them is, if at least one is positive, then at least one other one is negative. So this is the oriented matroid version of the basis exchange axiom. For valuated matroids, we're a very tropical audience here, so I don't need to spend a lot of time on this. We've got a valuated matroid is given by a basis valuation function, and it satisfies this min occurs at least twice condition when you do basis exchanges. So these look very parallel to each other. And what I want to do is kind of take the conceptual push out of these two and think about the space of oriented valuated matroids. So if you like hyperfields, this is a matroid with coefficients in the signed tropical hyperfield. Okay, now I've said what it is, or here's a different definition. So it's a function from E to the N to the real numbers that satisfies the alternating property. And it satisfies this exchange property, which says if I take one of the x's and move it over to the other side, and I look at all the ways I can do that, then the maximum modulus has to occur twice, at least, with opposite signs.
Is it possible that on the right upper part there is a plus without a pen?
Sorry, there's a what?
In the condition for valuated matrix might be a plus.
Well, I can take the exponential.
Okay, then R is also
yeah, you're right. Sorry about that. Thank you for catching my typo. Yeah, you're right. I should have had a plus there or changed the R to the non. Yeah, so, and what I'm going to say is if you take the sign of an oriented valued matroid, then you get back a chirotope. And if you take minus the logarithm, so I should change that to a plus, definitely, then I have a valuated matroid. So it's something which is both a valuated matroid and an oriented matroid in a compatible way. Right, so there's a space of oriented valuated matroids. These things naturally sit inside a projective space. So I'll call the space of these things OV. And this is a nice topological space, as opposed to the matroid Grassmannian, which is the nerve of a poset. So that's kind of a more combinatorial object that's harder to work with geometrically. So here's a theorem. First of all, the space of oriented valuated matroids is a fairly nice geometric object. It's what I call an exponential polyhedral complex, which means it's a cell complex. And under the logarithm absolute value map, each cell is mapped to something which is a nice piecewise linear polyhedron. So that's part one. And then part two is, this is the geometric model for the matroid Grassmannian. Okay, so the space of oriented valuated matroids is the thing that I prefer to work with. Although I've now come to I used to say I have no idea how to prove that E-infinity structure at the purely combinatorial level. Now I've realized, well, Laura Anderson pointed out to me that it is possible to translate what I've done to the purely combinatorial level. So I have to, in spirit of fairness, I have to admit that the use of oriented valuated matroids here is, for me, purely a conceptual convenience and not necessary. Just a homotopy equivalence. Yeah, I mean, these are, at the point set level, these are very different objects, but they're homotopy equivalent. Right. So the proof of this is you take the cell structure of the Dressian, and we have this map from the oriented valuated space to the Dressian. And you take the cell structure of the Dressian and lift that up to a cell structure on the space of oriented valuated matroids, and then do some analysis of that poset of cells and compare it to the poset of compare it to the poset of oriented matroids. So that's the proof idea. Right. Okay, so where does this E-infinity structure come from? Well, so I think this is the wrong audience to explain the details of E-infinity structures. And so instead, I'm just going to explain the homotopy commutativity, just the first level of that E-infinity structure. So if I have a map of ground sets, E including into F, as I have up here, then this induces a map of these spaces, these moduli spaces of oriented valuated matroids. So here's a proposition. If I have two maps, alpha and beta, and their images are disjoint, so I'm taking E and including it into F over here or down here, and those two images don't touch each other, then the induced maps of these moduli spaces are homotopic. So the proof idea is to write down a formula and then check that it works. So what I'm going to do is write down a one-parameter family of oriented valuated matroids, given the data of alpha, beta, and an oriented matroid mu on my ground set E. So starting with a matroid on E, I'm going to write down a one-parameter family of matroids from alpha pushing forward mu to beta pushing forward mu. And so here's the formula. So mu is some one of these alternating functions. So I need to define what it does on various input sets. So if I have a bunch of inputs and the first k of them, well, k of them are in the image of alpha, and the rest are in the image of beta, then I define it by this formula. Right? So if some of the inputs are in the image of alpha and the rest are in the image of beta, then I have some power of t, some power of 1 minus t, times the value of mu on those inputs if I pull them back from the image of alpha and the image of beta back to E. Right, so there's a formula. And so these guys are in the image of alpha, these guys are in the image of beta. And I define it to be simply 0 if the inputs don't satisfy that condition of being entirely in the union of these two images. Okay, there's my formula. And now I can vary t And the proof is just check that as you vary t, what you have is a one parameter family of oriented valuated matroids on the ground set F now. And it's just a little bit of tedious checking, but goes through. Yeah, so like this gives us the desired homotopy between these two things. And it's continuous in the input value oriented valuated matroid mu. It's continuous in mu. So this defines a homotopy between the induced map alpha star and the induced map beta star. Okay. So this slide is about building the higher homotopies. So if I have a d plus 1 tuple, then I can get a d simplex parameterizing a higher homotopy. We'll skip over the rest of this. Let's see. Yeah, so I'm going to skip over some of the infinity operad stuff here. Has anybody here seen the little discs operad? Just out of curiosity. One person. Two, maybe two? Okay, so maybe three. So for those people, and nobody else really, it's possible to build a combinatorial version of the little discs where instead of embedding little discs into big discs, we embed copies of the natural numbers into a copy of the natural numbers. So same idea as discs, but using the natural numbers. And this builds a combinatorial version of the little discs operad, which is an E infinity operad for parameterizing these structures, right? No more on that. I'll skip the rest of this slide. Sorry, I think I've finished far faster than I expected here because I'm trying to skip some of the topological details. Yeah, so let me go back and say, I described that homotopy if you have alpha and beta with disjoint images. And so you can use that homotopy to build up the homotopy commutativity. And in fact, you can build up all the higher homotopies from that as well. Yeah, so now I'll just finish with my last slide here. So if you've heard these words in topology, this E infinity structure tells us that the disjoint union of the matroid Grassmannians has this property called group completion. So given a monoid, you can turn it into a group. And given a topological up to homotopy monoid, you can turn it into a topological up to homotopy group-like object. And that's what's called an infinite loop space. And these are the things that represent objects in stable homotopy theory or generalized cohomology theories. So what we get is something, not matricidal, sorry. This is autocorrect. And every single time I typed matroidal, it somehow thought I meant to type matricidal. Yeah. So we get some kind of matroidal K-theory out of this. Now, matroidal K-theory may or may not be exactly the same as ordinary real K-theory. If McPherson's conjecture is true, then they are the same, and there's nothing new here. But if McPherson's conjecture is false, then this is some new cohomology theory that we can have fun exploring. So we don't know if these two K-theories are the same, but this is kind of a stabilized infinite limit version of McPherson's conjecture. Are these two K-theories the same or not? So yeah, if you can falsify this equality, then you falsified McPherson's conjecture. Right. Now, general homotopy types are much harder to work with than infinite loop spaces in generalized cohomology theories. So here, showing that these two things are equal is asking, are these two generalized cohomology theories the same? And generalized cohomology theories have lots of nice tools like Meyer-Vietoris property and that let you compute with them. So this might potentially be an appealing avenue to try to falsify McPherson's conjecture. I don't know, maybe it's still impossibly hard. I don't know, but it's at least potentially easier than just attacking it straight away in the unstable case. And here's a question that I like. Does matroidal K-theory have Bott periodicity? So again, if McPherson's conjecture is true, then there would be this thing called Bott periodicity. So Bott periodicity is what tells you that complex K theory is 2 periodic. So there's K0 and K1, and that's all there is. K2 is the same as K0. K3 is the same as K1. So in real K theory, it's an 8-fold periodicity. So the K theory, the real K theory of a point is Z2, Z2, 0, Z, 0, 0, 0, Z. So there's this famous 8-fold periodicity. After that, it repeats. So matroidal K theory may or may not have exactly that same 8-fold periodicity. If McPherson's conjecture is true, then it does have this periodicity. If McPherson's conjecture is false, then maybe it doesn't. Or maybe it does, even if McPherson's conjecture is false, right? So the possibility of Bott periodicity in this matroidal setting is something very intriguing to me. I'd love to explore that further. So one of the roots that it's a famous thing that like really elite level topologists always cut their teeth by giving a new proof of Bott periodicity. So there are like 20 proofs in the literature now, 30 proofs. So Atiyah, he was involved in giving at least 3 different proofs. And one of the most conceptually beautiful proofs of Bott periodicity goes by way of these things called Clifford algebras. So I think it'd be interesting to study matroidal Bott periodicity by trying to tropicalize Clifford algebras. So this is something that started with some undergrads that I had doing a summer project where they did some explicit calculations. We tried to tropicalize some Clifford algebras and see if the Clifford algebras have this thing called algebraic periodicity. Right, so Clifford algebras over the complex numbers come in a sequence. And it turns out that the nth one and the n plus 2th one they're not the same. They're not isomorphic, but they are Morita equivalent. They have exactly the same category of modules. So it'd be really cool if tropicalized Clifford algebras have that same Morita equivalence periodicity. So we're working on that. That's work in progress, and you can ask me afterwards if you want. But I think that's where I'm going to stop. And so apologies that I finished a little bit early there.